In instructional design, there's a pervasive assumption that the fastest way to teach an adult a new skill is to shove them directly into practice. We usually build a predictable architecture, a brief introduction to the concept, followed immediately by a cycle of exercises and tests. When designers try to break this cycle by building step-by-step demonstration examples, they hit a wall. Project managers look at the budget and argue that producing multiple examples slows down production and adds unnecessary instructional time without providing a measurable return. But forcing a beginner to immediately solve a complex problem creates a severe cognitive bottleneck. The mental effort required to figure out the solution consumes so much working memory that the learner has no capacity left to process and retain the underlying skill. The data points to a counterintuitive alternative. Replacing those initial practice cycles with completed, step-by-step worked examples actually accelerates the total training time and sharply reduces the rate of learner errors. We can track this effect back to foundational research from the 1980s. Cognitive researchers Sweller and Cooper split novices into two distinct groups. One group was assigned an all-practice track, solving 8 problems in a row. The second group received example practice pairs, where they studied a fully completed step-by-step example before ever attempting a similar problem. This chart reveals a dramatic difference. The practice group took 6 times longer to train than the worked example group. Critically, on the final test, the group that spent less time training produced a significantly lower error rate. They learned faster and performed better. This happens because of extraneous cognitive load. When a novice encounters a novel problem, searching for a solution maxes out their working memory. The brain is so busy hunting for the answer that it fails to recognize the structural patterns of the task. Studying a completed solution does the exact opposite. Because the answer is already provided, working memory is freed up. The learner can allocate their cognitive resources to mapping the underlying rules directly into long-term memory. Working memory is a strictly limited resource. To build competence efficiently, those resources must be allocated to studying structural solutions rather than blindly searching for them. Worked examples are not a universal fix, though. Their efficacy depends entirely on the complexity of the material relative to the learner's experience. This graph maps test scores of novices navigating easy and complex problems. For easy problems, practice exercises and worked examples yield similar results. But as complexity spikes, the success rate for practice exercises plummets, while those using worked examples maintain high test scores. However, if you force an advanced learner to study basic examples for skills they already possess, it actively damages their learning velocity. Cognitive scientists call this the expertise reversal effect. The detailed guidance becomes redundant, creating unnecessary cognitive friction. Instructional design requires precision. The learning architecture must dynamically adapt to the learner's pre-existing cognitive baseline. Early cognitive load research focused heavily on procedural, highly structured tasks like mathematics and physics. This created a misconception that worked examples only apply to rigid formulas. But corporate environments rely heavily on strategic tasks, fluid, dynamic scenarios that require interpersonal adaptation, like consultative selling or legal negotiations. For these skills, we use a modeling example, the strategic equivalent of a solved math problem, where an expert acts out a scenario. Observing this dialogue reduces the extraneous load of trying to invent the right words on the spot. This taps into the borrowing and reorganizing principle. Watching an expert model a behavior allows novices to borrow that strategic knowledge framework and adapt it into their own long-term memory. Modeled examples provide evidence-based blueprints for teaching dynamic, high-level soft skills, allowing learners to analyze an expert's execution without the pressure of live performance. There is a point of failure. If a learner passively watches an example or simply skims over it, the cognitive benefits drop to zero. To prevent this, the module must demand generative cognitive processing. The learner has to exert mental effort to actively decode the material. We engineer friction by integrating self-explanation questions into the interface. The phrasing is deliberate. It doesn't ask the user to parrot back what was said. It forces them to deduce why the action is important. When building these models, designers must be careful to avoid split attention. separating text instructions from the visual model forces the learner's eyes to dart back and forth, which creates severe cognitive overload. To solve this, we apply the modality principle. By using audio narration to describe the visuals, we distribute the information across both the auditory and visual channels, preventing either from overloading. An example is only effective if the architectural design explicitly forces the learner to actively decode the underlying rationale. The goal of example-based learning is not to eliminate practice altogether, but to systematically transition the learner into it. This requires an architectural sequence called fading. Fading carefully transfers the cognitive burden from the instructional system to the learner. After a fully worked example, the learner encounters completion examples. The system still handles the early steps, but the learner is forced to execute the final calculations or decisions. As the sequence progresses, the system gradually withdraws its support until the learner arrives at a pure, unassisted practice problem, allowing them to achieve full automation of the skill. This structure provides one final psychological benefit. Learners who progress through this guided sequence report a massive increase in self-efficacy compared to those subjected to trial and error methods. By managing cognitive load linearly, allowing novices to borrow expert models before forcing execution, we engineer a system that builds deeper technical intuition, faster, and with significantly higher learner confidence.